Hi, welcome to Random Walk with Varying Step Size, Take 1. In our previous video, we looked at a random walk to start to get a feel for Gaussian measurement errors. The model of measurement errors that we made in that video was crude. We looked at only the n most important sources of error. We approximated each of the n error sources as pushing the measured value q measured 1 unit up or down from the true value q true. So the error source was a constant size, in this equation denoted source size, times -1 or +1. We represented the sum of the n error sources as n arrows, all of the same length, pointed up or down. Then we calculated the sum of these n sources by simulating an n-step random walk. An error source that pushed q measured down was represented by a leftward step in the random walk, and an error source that pushed q measured up was represented by a step to the right. Adding up the n steps gave the result of adding up the n sources. So basically, in that crude model, q measured was equal to q true plus the constant error source size, represented by the constant arrow length, times the result of an n-step random walk. But real-world sources of measurement error don't typically act like this. Typically, the number of sources of error is huge. The different sources of measurement error will have different average sizes, and even a single source of error will vary from measurement to measurement. When we make a measurement, we don't know what it will be for that given measurement. So for one measurement, the error sources might look like this. If we measure the same quantity again, they might look like this. And if we measure it again, they might look like this. Okay, that was what we did before. Here, we're going to make an improvement on our crude model. We will again take our sources of error and make the approximation of only looking at the n most important sources. But this time, we will not take the step size to always be the same. Since we're interested in understanding Gaussian errors, we are interested in the case where the n sources of error have similar typical sizes. So we will take all n sources to have the same size on average, but we will let the size vary from trial to trial. Note that here we've shown the arrows as having all the same length, like we did before, but here we mean for them to only be the same size on average. We're still going to take each of the n error sources to be proportional to a step in a random walk. And those steps will still be randomly to the left or right. But we will be letting the step size in the random walk randomly vary from 0 to 1 instead of always being the same size. We will take the random walk step size to be flatly distributed between 0 and 1. This means, for example, that the probability that the step size is between 0.2 and 0.3 is the same as the probability that it is between 0.3 and 0.4. So this time, each error source will be a constant nominal error source size times a random number between -1 and +1. This is an improvement over what we did before when we multiplied the nominal error size by plus or minus 1. The nominal error size is something that would be determined by the experimental conditions of the measurement. While this is an improvement, it's still not a good model of measurement errors for most situations. We're interested in the case where the typical sizes of the main sources of error are similar, but them all having the same average size is not a common situation. Also, the flat distribution of error size between two set values would also not be typical in the real world. We will further improve on this model later. But in the next video, we will find one real-world situation where this model can be applied. It's a scenario where rounding error dominates the other sources of error. We will see Gaussian-like behavior emerge much more clearly in this case than in the previous random walk example. Here, we'll look at random walks with varying step size. We'll consider the cases of n equals 1, 2, 3, and 5 steps. Okay, let's start with a one-step random walk. The one-step case is not very interesting, but it is useful to cover it to show what we're doing. Like before, we'll drop a ball from the top. The triangle shows the range over which the ball can go, from x equals -1 to x equals +1. We have 10 bins at the bottom in increments of 0.2, from x equals -1 to x equals +1. Each ball that we drop represents an experimental trial where there is one important source of error. Here, we drop one ball. It ends up at x equals -0.481. This represents an experimental trial where the one source of error was -0.481 times the nominal error size. So Q measured equals Q true minus 0.481 times the nominal error size. Here we drop another ball. It goes to x equals minus 0.021. Okay, now let's drop 1,000 balls. At this rate, this simulation is going to take quite a while, so let's speed that up. We will plot the number of balls that end up in each bin at the bottom. On average, the distribution should be flat. The 10 bins are all equally likely. That means, on average, there should be 100 balls in each bin, but there will be statistical fluctuations. These fluctuations away from 100 balls per bin should be of order 10 balls. Okay, here's how this run of 1,000 balls turned out. The number of balls in a bin ranged from 88 to 116. This is compatible with a flat distribution, which is what we wanted. That gives some confidence that we know what we're doing. Okay, since that worked, let's look at the n equals 2, two-step case. Here's the setup for the two-step case. Each ball that we drop represents an experimental trial where there are two important sources of error. The two-color triangle structure shows the range that the ball can take at each step. After the first step, the ball can have a location anywhere between x equals -1 and x equals +1. This range is shown in white. After the second step, it can be anywhere between x equals -2 and x equals +2. This is shown in blue. The bins are in units of 0.2. Let's drop a ball. Its first step is -0.967, and its second is -0.200, so it ends up at x equals -1.166, shown at the bottom of the screen. This represents an experimental trial where the first error source was -0.967 times the nominal error size, and the second was -0.200 times the nominal error size. So, in this hypothetical experimental trial, Q measured comes out to be Q true minus 1.166 times the nominal error size. Now we drop a second ball. Its first step was plus 0.242, and its second was minus 0.148, so it ended up at x equals 0.093. Okay, now let's drop 2,000 balls. And while that's running, we'll figure out what the distribution should look like on average. Let's make a plot. On the horizontal axis, we'll put the result of the first step, which we'll call S1, and on the vertical axis, we'll put the result of the second step, which we'll call S2. If we drop many balls, they should evenly cover the square, demarcating the region where both S1 and S2 are between -1 and +1. Here, the S1 and S2 axes have tick marks in units of 0.2. Now, we want to know the probability of a ball ending up in a particular bin after the two steps. The location X that it ends up at is S1 plus S2. To look at the location X after the two steps, we draw diagonals. For example, if we want to look at those balls which end up between x equals 0.2 and x equals 0.4 after two steps, we look at those which fall between the lines S1 plus S2 equals 0.2 and S1 plus S2 equals 0.4. This area is shown in blue. Now, to figure out the probability of the ball ending up at a value of x between 0.2 and 0.4, we look at the proportion of the square taken up by this blue strip. We can similarly do the same for any other bin in X. So, we've transformed this probability problem into a geometry problem. By looking at the areas of these diagonal strips, you can convince yourself that a plot of the probability of the ending location of the ball, here denoted P of x, will take a triangle shape. So here's that plot. A triangle shape is what happens on average. This is clearly not a Gaussian, but it is peaked in the middle of the distribution. Okay, let's look at the results for this run. We can see the triangle behavior. Okay, and with that, it's time to move on to the three-step case. Here is the setup for 3 steps. Here, let's drop one ball. The steps it took were minus 0.703, minus 0.061, and plus 0.076 to end up at x equals minus 0.687. Okay, let's drop 5,000 balls. It's more difficult to derive the shape for the average case here than it was for n equals 2. So let's plot it. Okay, here's the probability of the ball ending up in each bin. Let's remind ourselves what we saw for the 3-step random walk where the step size was fixed. That didn't look very Gaussian at all. Clearly, the new results are showing much more Gaussian-like behavior. Remember, we're trying to test the assertion that as the number of steps n gets large, the probability distribution approaches a Gaussian. We are seeing a nice bell curve here, even though we're only looking at n equals 3, and 3 is not a very large number of steps. Here we've plotted the average case with an actual Gaussian curve superimposed. Discrepancies are clearly visible, but again, this is only after 3 steps. It's not a Gaussian, but the resemblance is clear. Okay, that was what we get with very large statistics. Here are the results of this run of 5,000 balls. Okay, finally, let's look at the 5-step case. Here's the setup for 5 steps. Let's drop just one ball to see what happens. Okay, now let's drop 5,000. We'll plot what happens on average. Here's the probability distribution for n equals 5 steps. Again, let's compare this with what we saw in the previous fixed step size random walk. Well, the fixed step size is peaked in the middle, but it's hard to call it Gaussian. The new results are much more Gaussian-like. Here, we've plotted a Gaussian curve on top. We can see improvement over the n equals 3 case. we can see some discrepancies, but it's good to keep in mind that even n equals 5 is not large. Okay, here are the results of the current run. Even with these statistics, we can see a Gaussian-like shape emerging. Okay, so we've looked at a random walk with a varying step size for the cases of n equals 1, 2, 3, and 5 steps. Let's look at what we've done and see what's coming next. Here, we've made an improvement over our previous modeled Gaussian errors. Before, all n sources of error were the same size, but were randomly up or down. Here, we've taken the n sources to be the same size only on average. Both their sizes and directions vary from trial to trial. This is still not a good description of typical scenarios with measurement errors. Usually the main sources of error wouldn't have the exact same typical size, and usually the error from a given source wouldn't be flatly distributed between two endpoints, like we had here. So this model is still, for the most part, a bit artificial. But in the next video, we'll see a scenario where what we've done here does actually apply to a good approximation. We'll be looking at the case of rounding error on a set of measurements, and this will be our first example of real-world Gaussian errors.